When people hear that scientists can grow a diamond worth $50,000 in just a few weeks, the reaction is usually disbelief. Diamonds are supposed to take billions of years, crushed deep beneath the earth under impossible pressure, guarded by geology itself. Yet inside modern factories, diamonds are now grown not by tectonic plates, but by engineers in lab coats, staring at plasma through reinforced glass. At the heart of this transformation are two fundamentally different approaches to diamond creation: HPHT and CVD. HPHT, or high pressure, high temperature, is the older method. It was developed in the mid-20th century when scientists first figured out how to mimic the conditions found roughly 150 kilometers below Earth's surface. Inside a refrigerator-sized press, carbon is dissolved in molten metal and subjected to temperatures between 1,300 and 1,600 degrees Celsius, while being crushed under pressures approaching 870,000 pounds per square inch. That's pressure so intense it would instantly flatten anything not designed to survive it. CVD, or chemical vapor deposition, is where the modern diamond revolution truly begins. Instead of recreating the Earth, CVD rewrites the rules entirely. The process starts with something deceptively small: a diamond seed, often no larger than a postage stamp, typically around 10 by 10 millimeters. This seed isn't synthetic in the sense of being fake. It's real diamond, usually cut from a previous growth cycle. The chamber is evacuated of air and filled with a carefully controlled mix of hydrogen and methane gases. Hydrogen makes up the vast majority of the environment, while methane, the carbon source, is present in extremely small concentrations, often less than 1%. Then microwaves are fired into the chamber, not to heat it like a kitchen appliance, but to strip electrons from the gas molecules. This creates a glowing plasma cloud that looks like something pulled straight out of a sci-fi movie. Inside that plasma, methane molecules are torn apart, releasing individual carbon atoms. Those carbon atoms don't fall randomly. Under the right conditions, they rain down onto the diamond seed and lock perfectly into the existing crystal lattice. Atom by atom, layer by layer, the diamond grows. Not melted, not pressed, grown. The temperatures inside the chamber hover between 800 and 1,200 degrees Celsius, far cooler than HPHT, and the pressure is lower than Earth's atmosphere. This is controlled growth at the atomic level. What most people don't realize is how slow and deliberate this process still is, even with modern technology. A high-quality CVD diamond might grow only a fraction of a millimeter per day. After several days, the growth is paused, the diamond is removed, inspected, and polished to correct microscopic imperfections. This step is critical. If defects are allowed to propagate, they can distort the crystal structure and reduce clarity. After polishing, the diamond goes back into the chamber for another growth cycle. This stop-start rhythm continues for 3 to 4 weeks until the stone reaches its target size. By the end of the process, what emerges is chemically, physically, and optically identical to a mined diamond. The carbon bonds are the same, the hardness is the same, the refractive index, the thing that makes diamonds sparkle, is the same. Even trained gemologists require specialized equipment to distinguish a CVD diamond from a natural one, and organizations like Gemological Institute of America certify both using the same grading standards of cut, color, clarity, and carat. So how does this translate to a $50,000 stone? Size and perfection. Large, flawless diamonds are rare in nature and difficult even in laboratories. Growing a diamond without nitrogen contamination, crystal strain, or internal defects requires extreme precision. The larger the stone, the more opportunities there are for something to go wrong. That's why a high-clarity, colorless CVD diamond weighing several carats can command prices rivaling or even exceeding natural stones, especially in industrial or optical applications where purity is everything. Beyond jewelry, lab-grown diamonds are reshaping entire industries. Diamond is not just beautiful, it's one of the best materials known to science. It has extraordinary thermal conductivity, extreme hardness, chemical inertness, and the ability to function as a semiconductor. CVD diamonds are now used in high-power electronics, heat sinks for advanced chips, quantum computing substrates, medical imaging windows, and even next-generation cutting tools. In many of these applications, natural diamonds are actually inferior because their internal impurities can't be controlled. Economically, the implications are massive. Traditional diamond mining requires enormous capital, environmental disruption, and geopolitical complexity. CVD factories, by contrast, can be built anywhere with sufficient electricity and technical expertise. This is why countries like India have become global leaders in lab-grown diamond production, operating massive facilities where hundreds of reactors run simultaneously, each quietly growing stones around the clock. But this isn't cheap manufacturing. A single microwave plasma reactor can cost hundreds of thousands of dollars. The energy demands are significant. Skilled technicians monitor gas ratios, plasma stability, and growth rates constantly. One mistake, a pressure fluctuation, a gas impurity, a power interruption can ruin weeks of work. That's why, even though the timeline is measured in weeks instead of geological epochs, a perfect diamond is still a triumph of patience and precision. There's also a philosophical shift happening beneath the surface. For over a century, diamonds were marketed as symbols of rarity and permanence, tied to the idea that their value came from being ancient and scarce. Lab-grown diamonds challenge that narrative. They suggest that value can come from mastery rather than extraction, from knowledge rather than accident. The carbon atoms in a CVD diamond don't care whether they were assembled under Africa or inside a steel chamber. The physics is the same, and yet the romance remains, because even in a factory, growing a diamond is not guaranteed. Each stone is a small experiment in controlled chaos, balancing chemistry, physics, and time. When a flawless crystal emerges after weeks of growth, it represents not just wealth, but the edge of human capability, our ability to take one of nature's most extreme creations and reproduce it, atom by atom, with intention. That's the real story inside a CVD factory. Not shortcuts, not fakes, but one of the most advanced manufacturing processes ever developed, quietly turning methane gas into something that can outlast civilizations. And all of it happens in about 3 weeks. What makes this even more astonishing is how controlled the environment inside a CVD reactor must be to maintain that perfect lattice structure. A diamond is not just compressed carbon, it is carbon arranged in one of the most rigid and symmetrical crystal structures known to science. Each atom forms 4 covalent bonds in a tetrahedral geometry. If even a small number of atoms attach incorrectly, strain lines form. If nitrogen slips into the chamber unintentionally, it can tint the diamond yellow. If boron is introduced deliberately, it can create rare blue diamonds that conduct electricity. This is where CVD becomes more than jewelry manufacturing. It becomes materials engineering. By tweaking methane concentration, plasma density, substrate temperature, and chamber pressure, scientists can influence growth rate and crystal purity. It's a constant trade-off between time and perfection. For a high-value $50,000 gem-grade stone, perfection wins. Inside large commercial facilities, dozens, sometimes hundreds, of microwave plasma reactors operate simultaneously. Each chamber glows with a bright violet-white plasma dome hovering above the diamond seed. The glow isn't decorative, it's ionized hydrogen stabilizing the growth environment. Hydrogen plays a critical role in suppressing graphite formation. Without hydrogen, carbon atoms would arrange into softer graphite instead of diamond. Operators monitor each reactor through thick quartz windows and digital dashboards tracking temperature stability within just a few degrees. Infrared sensors measure substrate temperature continuously. Gas flow controllers regulate hydrogen and methane down to tiny fractions of a percent. Pressure gauges ensure the vacuum remains stable, and that comparison isn't accidental. CVD technology shares roots with the same vacuum deposition processes used in advanced chip manufacturing. The difference is the material. Instead of silicon wafers, the substrate is diamond, And that's why tech companies are increasingly interested in synthetic diamonds, not for rings, but for hardware. Diamond can dissipate heat better than copper. In high-power electronics, electric vehicles, 5G infrastructure, military radar, overheating is a major limiting factor. Thin diamond layers grown via CVD can dramatically improve heat management, extending device lifespan and efficiency. But back in the jewelry world, scale is what separates a 1-carat stone from a 5-carat masterpiece. Growing larger diamonds requires longer cycles and extremely stable plasma conditions. As the diamond thickens, internal stresses build. Scientists must periodically remove the stone, polish its surface flat again, and reintroduce it into the chamber. Each pause adds labor cost, each growth cycle adds energy cost, and each additional week introduces risk. That's why a 3 or 4 week timeline for a large, high-clarity CVD diamond is actually considered remarkably fast. HPHT, by contrast, operates on a completely different philosophy. Instead of plasma and vacuum chambers, HPHT relies on brute geophysical mimicry. Massive hydraulic presses squeeze carbon with unimaginable force while heating it in molten metal catalysts like iron or nickel. The molten metal dissolves carbon and transports it to a cooler region inside the press, where it crystallizes as diamond. It's an elegant reproduction of mantle conditions, but scaling up gem-quality clarity is difficult because metal inclusions can become trapped inside the crystal. Interestingly, some manufacturers combine both techniques. A small HPHT-grown diamond seed might serve as the starting substrate for CVD growth. This hybrid approach leverages the structural integrity of HPHT crystals while using CVD for cleaner, larger-scale expansion. Beyond the factory floor, there's also the environmental narrative. Traditional diamond mining involves removing tons of earth for a single carat of gem-quality material. It requires heavy machinery, water diversion, and often long supply chains. Lab-grown diamonds consume significant electricity, especially for plasma generation, but their footprint is more predictable and increasingly powered by renewable energy in some regions. Then there's traceability. A lab-grown diamond has a fully documented origin. Its growth cycle, reactor number, and production batch can be tracked precisely. This transparency appeals to younger buyers who value sustainability and ethical sourcing. Yet despite all these technological and ethical advantages, the perception battle continues. Some consumers still equate rarity with value. Natural diamonds formed over billions of years carry a narrative of deep time and geological wonder. Lab-grown diamonds represent human ingenuity and controlled creation. The emotional preference often determines the purchase. But in terms of physics, the debate ends quickly. Under a microscope, the carbon lattice in a CVD diamond is indistinguishable in fundamental structure from that of a natural stone. Advanced spectroscopy can detect subtle growth patterns unique to lab conditions, but these are identification markers, not quality differences. And that brilliance comes down to atomic perfection. Light entering a diamond slows dramatically due to its high refractive index, bending and reflecting internally before exiting as intense sparkle. The more flawless the crystal, the fewer interruptions light encounters. CVD technology, when carefully controlled, produces exceptionally clean stones because the growth environment is isolated from geological randomness. Now consider economics again. If a reactor can produce a multi-carat diamond worth tens of thousands of dollars in under a month, and that reactor runs continuously throughout the year, the production capacity becomes enormous. That's why the best CVD facilities resemble research laboratories as much as factories. Teams of materials scientists analyze crystal samples, adjust recipes, and refine plasma parameters constantly. Each improvement might increase clarity by a fraction or speed growth by a few percent, but over thousands of stones, those improvements compound into massive competitive advantages. There's also a frontier beyond jewelry entirely: quantum technology. Certain diamond defects, such as nitrogen vacancy centers, can be engineered intentionally inside CVD diamonds. These atomic scale defects can act as quantum sensors capable of detecting magnetic fields with extreme precision. In laboratories, diamonds are being used to develop next-generation quantum computers and ultra-sensitive medical imaging systems. So when you hear $50,000 diamond in 3 weeks, it's tempting to focus on speed or price. But the deeper story is about control, the human ability to manipulate matter at the atomic scale. CVD growth represents a shift from mining what nature happened to make to designing what we need from first principles. In 3 weeks, methane gas becomes a crystal harder than any other natural material. In 3 weeks, invisible carbon atoms arrange themselves into a structure that can last longer than mountains. In 3 weeks, a glowing plasma cloud inside a steel chamber produces something once thought possible only under crushing planetary forces. And perhaps that's the most remarkable part. Not that diamonds can be grown quickly, but we now understand nature well enough to replicate one of its most extreme creations, atom by atom, on demand. Inside the CVD factory, the glow never stops. Reactors hum quietly. Engineers watch plasma flicker like controlled lightning. And somewhere in that chamber, carbon is becoming something extraordinary. Not over billions of years, but in just a matter of weeks.